Hello everyone, and welcome back to the series of lectures on actinide chemistry. In the last lecture, we have left on the studies, that is the absorption studies of lanthanides and actinide. And in this particular table, I have given you the lambda max as well as the epsilon max, that is the molar absorbability of different actinides in 1 molar perchloric acid. And you can see that many of the actinides is having very high Emax, but suggests that you can measure even a very small quantity of these actinides using UV spectroscopy. And in application part, we have already discussed what are the kind of applications you can think of using absorption spectra. The first one is like quantitative analysis. You just want to have an idea of the oxidation state. You can also do some quantitative analysis, provided the medium in which we want to do the quantitative analysis, you should be having epsilon in that particular media. So if you are knowing that epsilon values, you can do some kind of quantitative analysis also. I have given you some example of the redox reaction also, where I have shown you that one can study the kinetics of the redox reaction using UV spectroscopy, and the complexation of metal ion using different ligands, as we've seen in the previous slides, that once these ions make a complex with the different kind of ligand under a given set of conditions, their absorption spectra will change, and based on that changes, if you do a titration that I've shown in the figure here, in which I have shown you that if someone starts with some concentration of neptunium and do the titration with some ligand, there is a shift of the peak that occurs at around 976 to 991, and if one does the titration, then by fitting the titration data into, there are certain software that comes for that, and you can fit the data, and it is simply based on the Lambert-Beer law, and you can get an idea about the stability constant of this complex just by using the spectrophotometric titration. You can also get estimation of the lanthanides and actinides that are present in the environmental sample in a very small quantity. In cases when the quantity is so small, then we generally prefer to use some kind of chromophoric reagents, which again having very high Epsilon value, and because of their very high Epsilon value, you can go to a very low concentration. With that, we'll move to the other spectroscopy, that is called emission spectroscopy. So there are certain terms that you may be familiar with, but I'll just give a brief note on these different terminologies. The first one is absorption, as we have already discussed that what I mean by the absorption spectra. And the next term is like excitation. So does the excitation spectra and the absorption spectra are same? The answer is not exactly, because let us assume that you have a species. You have a species which has spectra absorption, let us say A. In your absorption spectra, you are exciting with certain wavelength of the light. So you are getting this kind of spectra, wavelength versus your intensity or your absorbance of suppose some species A. But in your excitation spectra, when we read that how to record the excitation spectra, then you'll find that whatever peaks are coming for the absorption spectra may not be coming exactly same for the excitation spectra. That we'll see in the coming slides, that how the excitation spectra is recorded, and once you know how the excitation spectra is recorded, you can very well understand that why there is a difference between the absorption spectra and excitation spectra. You can say that emission spectra is again, if you see the simple Jablonski diagram here, we know that absorption starts from ground state to any one state, that is can be like some singlet 1, singlet 2, and there with the vibronic relaxation it comes back to the ground state of the first excited state, and from there they can either go by intersystem crossing to the triplet or they can come back. And this kind of coming back, generally if it is a radiative process, it will emit some kind of radiation which are generally recorded, and if they are falling in the region that is UV visible region, then we say it is a luminescence, and depending on the time at which the decay is taking place, it can be a fluorescence which is having a very short period of time after excitation, whereas if the time is long, basically in those cases it is going from singlet to triplet, and from there it is coming back. In those cases generally it is phosphorescence, which is called sometimes delayed fluorescence also. So I hope you have these terms in your previous classes, so you can better understand them. With that, we can just see that what are the sources that one can use for the emission spectroscopy. So here I have given you the basic setup. In a normal fluorometer, one would have an excitation source, and then obviously out of certain bunch of radiations you select one for your excitation, and then you put your sample. There is radiation will excite your analyte from the ground state to the some state of singlet, and then from vibranic relaxation they will come here, and then from there they will emit. But you see that here, if you see the geometry, you will find that my detector is kept 90 degree to the sample chamber. Why it is? Because this intensity is too large. So if you are keeping detector here, and whereas the emission signals are very weak, so if you are keeping detector in this region, you will be only recording the excitation source spectra. You will not be able to get emission profiles. So for that reason, to avoid this intensity from the source, we use to put the emission detectors at 90 degree, and from there you select the emission monochromator, you record the emission spectra, and you get spectra. So depending on the excitation sources, as I've told you that you have to excite first. You have to excite your molecule from the ground state to the excited state. So depending on the excitation source, you can have different kind of luminescence. Yes, such as some of them I've given, like cathodoluminescence, in which one use the electron beam as an excitation source, or X-ray or a particle. If you use these kind of sources for your excitation, they are called radioluminescence. If you are using electric field, then it is electroluminescence. So depending on the nature of your source that you are using for the excitation, you can have a variety of luminescences, starting from cathodoluminescence to thermoluminescence. And in this particular, we are mainly interested in photoluminescence, where we are using photon, or you can say the light source, as a excitation. So when we have this excitation, or you excite with some photons, then what kind of information that we can get? So again, you excite, and then from the ground state of the excited state, it is emitting. So what kind of spectra we can record? We can record something that is called excitation spectra. We can record emission spectra. Besides that, we can also record lifetime. And so these techniques give you triple resolution. One, you can have some information from the excitation, you can have some information from the emission spectra, and you can have an added information from the lifetime also. And this generally has very high to signal noise ratio, and many a time it is a non-invasive and non-destructive technique. So what we can do and how we are doing, that we'll try to see in the next slide. So if you talk about the lanthanides and actinides, so as we see that in the lanthanide, the energy level are quite far away as compared to the actinides, or rather you can say the actinide possesses a ladder-like pathways. So what happens because of this ladder-like pathways in the actinides, when you are exciting from the ground state to any upper state, then most of the photons come back to the ground state just by a non-radiative decay process. So they are not fluorescent, or many of the actinides you will not get any fluorescence. Whereas in case of lanthanide, this kind of ladder-like pathways are missing, and because of that, we can see most of the lanthanides give very good luminescence. And in actinide, you are having luminescence mainly from americium, curium, and uranium. And for others, although they can give you some sort of emission line, but they are lying basically in the NIR region. So we cannot say that they are fluorescence. So in fluorescence region, we are mainly getting three, that is americium, curium, and uranium, because these are the one who is emitting in the region that is the visible region. We have already discussed about the atom symbols, so I am not going into the details, but I just want to add that since we are going to study about the luminescence, and here I am using europium as a example. So I just want to have a look on the states that europium do have. And as we have discussed that with the F6 configuration of europium 3 plus, we are having a 7f state, and in 7f state we are having certain J levels, and those levels are 7f0 to 7f6. And we have also seen that out of these levels, which is the ground state, though 7f0 is the ground state and 7f6 is the high state in this 7f level. So let us understand first that okay, how one record the excitation spectra or the emission spectra before going to study the in detail about the europium spectra. So here I have given you some of the emission spectra of different lanthanides, and you can see that many of the lanthanides do emit in the region that is visible region. You can see this region or this region. So they emit, and some of them basically emit in NIA region also. So most of the colored compound are generally emitting in this region, as you can see here also that europium is generally reddish color, so that is coming from its emission, most of the compound of europium. And terbium is again green, so you can see the emission is in the green region. So first thing I would like to tell you that how we record this kind of spectra. So as I've shown you that you have a source, then since we are doing a photoluminescence, our source is xenon lamp in this case, and then depending on your metal ion, suppose I'm using europium, so depending on your metal ion you put a monochromator and you choose certain wavelength. So for europium we choose wavelength of around 394 nanometer. If you remember, then in the absorption spectra of europium I have shown you that this transition that is happening at 394 is basically starting from 7f0 and going to 5l6. So this is the transition that is happening place at 394. So we are using this transition for the excitation, and once you excite, then there is obviously some emission spectra. So what we are doing to recording for the emission spectra, we want to record the emission spectra, and what we are doing, we are first fixing the excitation wavelength. In this case I fix at 94 nanometer, and then I excite and I scan the emission monochromator to get emission spectra, and then I get certain lines here. So this is the intensity and this is the emission line we get. So for emission spectra we are fixing the excitation wavelength. Similarly, if I want to record the excitation spectra, here I will also tell you about the difference that you can understand from the absorption spectra and excitation spectra. So suppose I want to record an excitation spectra, I want to scan the excitation wavelengths. First I have to fix the emission wavelength. For europium, let us say we fixed it at certain value. Now what will happen, you have fixed this path. What does it mean? That suppose you excite at certain wavelength, you can only see peaks in the excitation spectra when you are seeing emission here. Suppose I have 3 peaks in the absorption spectra, in the UV absorption spectra, but even after excitation using this peak I am not having any emission at 612. I will not see this in the my excitation spectra. Now I will try to excite at this. Suppose you are exciting in this region and you are able to get some peak, then you will see that. So only those peaks are visible in the excitation spectra which give luminescence at whatever fixed wavelength you have chosen. So in absorption spectra you may get more than one lines, but it doesn't mean that all those lines are giving you the emission profile. So by fixing the emission at a given wavelength, when we scan the excitation monochromator, we are getting some excitation spectra. Now we are having excitation spectra and we are having emission spectra. Let us say that we are having excitation spectra of kind. So this is my emission spectra, in which we are getting a peak here. again we are having an so this is my emission spectra, and again we are having some excitation spectra in which I am getting peak at 394 nanometer. So now I am having an emission spectra, I am having an excitation spectra. What I will do, I will choose the peak maximum, whatever is getting in the emission spectra, and the peak maximum whatever I am getting in the excitation spectrum, and these two positions I am using to find out my lifetime data. So what I am doing in the lifetime data, I am using excitation source at 394, emission line at 612, and both I am fixing before recording the lifetime spectroscopy. So by fixing these we record the lifetime. So this is the way we record these three kind of spectra, that is the excitation spectra, emission spectra, and the lifetime spectra. And what are the kind of information that we can get from this kind of spectra, we will discuss in the next slide. And here also I have just shown you that different ground state term symbol that you have derived using the term symbol recipe that I have given in the last lecture. So you can easily follow that and you can derive most of this term symbol using that recipe. So now, since I have told you that we will discuss about the europium, but before going to the discussion, I will just show you certain important things that one should be able to understand before plotting or before recording any kind of emission spectra. The first thing is you should be having a knowledge of the different kind of levels. You should know that what is the ground state, what is the first state, what is the second state. So this information we should be having, and when you are exciting, then before the excitation the first question comes at what wavelength, because if you are given a sample you don't know what is the wavelength at which I have to excite, then what to do? You can take help of your absorption spectroscopy, and as I have shown you that in your absorption spectroscopy you may be having more than one peak. You have to try at different peaks, and you have to try at different excitation wavelength, and then you scan the emission, and at whatever wavelength you are getting good emissions, you can say that okay, this is the excitation wavelength for this particular metal ion. But how to write the transition? Suppose I write that I am exciting from here. Suppose this is my ground state, that is 7F0, and I am exciting and going to, let us say here, as I said that we go to 5L6, some state suppose I am going. So how to write? So there is a way to write that. We can write like 7F0 to, let us say 5L6, or we can also write 5L6 and then we can put an arrow like this and we can write 7F0. So what is the right way of writing? How do we represent this transition, that okay, this is my absorption transition and this is my emission transition? The rule is that whenever you want to write, either you want to write an absorption transition or any emission transition, you should always take care that your high energy state should be always at left hand side and your low energy state is on the right hand side. What does it mean? That if you see this notation, my high energy state, my 5D0 is high energy state. My high energy state is on the right side, which is wrong. Your low energy state should be on the right hand side. So this notation is wrong. So what we have to do, we have to always keep this in mind, that whenever we are writing, my low energy state should be on the right hand side. So what is my low energy state here? My low energy state here is suppose 7F0. So this is my low energy state. This should be on the right hand side, and my high energy state, suppose I am doing some 5D0, this should be on the left hand side. And when I am doing any kind of absorption, since it is my lower state, I have to write like this. Suppose I want to write about the emissions, then these things you have to write like this only, that your low energy state is on the right side, but since you are talking about emission, you have to write like this. So only the sign, only the arrow will change, the state's position will not change. So even in the recent literature I have seen lots of people do not follow this notation, but I think it is a good habit that if you start following this habit, that whenever you are writing, you should be cautious that always your low energy state should be on the right hand side. One more thing, that many time whenever we are plotting, we use wave number or sometimes wavelengths, but in general convention one should plot always in wave number scale. with the highest wave number on the left hand side and the lowest wave number on the right hand side of the spectrum. So this is a very typical spectrum of the europium that I have given here. If you see that it has several lines that arises from the transition from 5D0 to different state, that 7F0 to 7F1, 7F2. So all these transitions, so you can see from this diagram very well, you have excited from 7F0 to 5L6. So you have excited to 5L6. Now they are emitting. Their emission is taking from 5D0. So when they are emitting, you are getting a peak that is from 5D0 to 7F0. That generally we say that is a kind of 0-0 peak. Then 7F1, 7F2. So like that, you start from 5D0 and you are getting all these peaks. That is 7F0, 7F1, 7F2. So when you are getting these peaks, what does they mean? But you can understand that these peaks are coming from the FF transitions, right? So you can have some idea about the energy levels of the metal ion, of the atom you are probing. You can also see that when we are moving from the 7F0 to the 7F4 states, you can see the distance between the J's and J plus 1 lines. If I say the distance between F0 and F1 line, if you see the distance between this F0 and F1 line, they are very close to each other. But the moment you go for higher, so when I say higher means, suppose you are instead of 5D0 to 7F0, now you are seeing distance between 5D0 to 7F6 and 5D0 to 7F5 transition. So when you are measuring at the higher J value, you are finding that the distance between the two J lines is increasing. This is coming from the Landy interval rule, that the interval is increasing as we are going from the left hand side to the right hand side, or you can say the splitting has increased when we are moving towards the higher J values. And this transition that we are getting in the luminescence, they are mainly known as induced electric dipole transition, and their origin is mainly due to the interaction of the lanthanide with the electric field vector through the electric dipoles of the electromagnetic radiations. And when you talk about this transitions, they are again laboratory forbidden, so their intensity is also not very good, but still you see that because of certain intermixing of the different state. Since these are laboratory forbidden and they are very weak, so this is called induced electric dipole transition. But one more transition that you can see is called magnetic dipole transitions. These transitions are largely independent of the environment of the lanthanide ion, and sometimes they are also used an internal reference for your spectra. These are some of the selections rule that is given for electric dipole, magnetic dipole, as well as induced electric dipole transition. And as I showed you that all these transitions are of not same nature. Some of them are electric dipole and some of them are magnetic dipole. And here I've just given you the list that if you see that the transition that is 5D0 to 7F0. So if you see this emission line from 5D0 to 7F0, this is electric dipole. But the second one, that is the 5D0 to 7F1, that is a magnetic dipole. When I say magnetic dipole, it means its intensity do not have very much variation when we are changing the ligand field. And rest other you can see these are electric dipole transition. So many times this transition, that is 5D0 to 7F1, are used as an internal standard when we are trying to compare different systems of same ion, and we'll try to understand what is the ligand strength and how the ligand is doing splitting and what ligand is doing what kind of splitting. So sometimes we use this kind of magnetic dipole transitions for understanding of the ligands or the symmetry around the metal ion. These are some of the selection rules that is generally comes from the quantum mechanical calculation, that what kind of transitions are allowed and what kind of transitions are forbidden using this set of rules that are called selection rules. And depending on the selection rule, those transitions who follow the selection rule, they are intense, whereas those transitions who do not follow this selection rule, they are either they do not happen, or if there is some intermixing between the different F states, they have certain probability of happening, and because of that they get some intensity, but again it is a very poor intensity. So we'll now discuss about the application of emission spectra. Once we have emission spectra recorded, what are the kind of information that you can draw from the emission spectra? The first information you can easily draw whether you have different complexes or the same complexes. When I say different complex or the same complex, my metal center is same. When I say different, I mean the symmetry around the metal ion. So suppose you are having a complex, let us say europium, with three different ligands, that is L1, L2 and L3. But you can see directly from this figure that although they are having europium in the center, but the peak intensities and the splitting and the pattern is quite different from each other. So just by looking at this spectrum, what information you can directly derive is that the symmetry around europium ion in the three systems are different. So this is the direct information we can get. Suppose you want to have information about the stability, then you can take any one system, and as we are doing titration in the absorption spectra, you can do some sort of titration here also, and from the titration data you will get the stability constant of that particular complex. So this can also be used for the calculation of the stability constant. You can also use this kind of spectroscopy for the detection of lanthanide and actinide in the environmental sample, and detection of uranium in various kind of environmental sample using laser fluorometry, which is a kind of emission technique, is very common. So this is also used for the understanding of symmetry as well as for the quantification of the metal ion into the environmental samples. They can also tell you about the symmetry, exact symmetry around the metal ion. As I said that you can say the symmetry is different, but what is the symmetry? That you can tell using this emission spectra that will come into the next slide. But before that, as I told you that you have certain peaks, and out of those peaks, the peak at 7F1 is magnetic dipole, rest others are electric dipole. So if you take the ratio of the magnetic dipole transition to the electric dipole transition, you will get something that is called as asymmetry ratio, and this asymmetry ratio is very important when you want to understand the symmetry around the europium ion. It so happens that this ratio is very high when the symmetry is very low, and the ratio is low when the symmetry is higher. For example, in water, where the symmetry is very high, this ratio is around 0.5 to 0.6. So this asymmetry ratio can be used to understand, at least to say that whether the symmetry is high or the symmetry is low. But what is the exact symmetry? To get that information, we have to look this table. So as we have known that when we are having some states, let us say 7F0 or 7F1 or 7F2, any state that we are having any term symbol. So we have seen that okay, these are getting split because of LS coupling. But what about this state? They further get splitted because of the JJ coupling, and what we get, the splitting is nothing but 2J plus 1. So you can say the 7F1 can split into 2J plus 1 means like 3 another state. So that is 7F plus 1, 0 and minus 1. So you can say that all the J states can further split depending on the field around them, depending on the electric field around them. So from this splitting pattern that we get in the J, we can understand what is the exact symmetry class of that particular metal ion, or what is the symmetry around that particular metal ion. One thing you have to take care that you can just tell about the symmetry class. You may not be able to tell you about the exact point group what belongs to, because for a given point group the splitting pattern is identical. So you may not be able to get exactly whether it is D4H, D4 or D4V, but you can certainly say that yes, when we have certain splitting, suppose you are having this splitting that the first peak is monosplitted and this is the 2 and this is 4, so you are having this kind of splitting pattern, you can definitely tell yes, the europium is having a tetragonal environment. But exactly it is D4H and D4V, it is not that easy to tell, but people try to tell that using studies at low temperature, but that require a lot of experience and it's not that straightforward. But you can at least have an idea about the class, symmetry class, using just by looking at the splitting of the J level. So here I have given some example that how they look like. So suppose we have splitting in this 7F2 level. Here you can say the maximum is 5, and to get maximum you should be having symmetry in the triclinic region, where you can say that 7F2 should be 5. So the more unsymmetric the environment, more is the JJ splitting. So triclinic is the less asymmetric or the most asymmetric. So we are getting 5 peaks here, and you can say 7F1, which has maximum JJ splitting of 3. You are getting 3 peaks. So like that, if you are doing studies at a very low temperature, you can get these fine splittings, and from this number of fine splitting of different J levels, you can get information about the class, the symmetry class of European man, that what is the symmetry around the European man in this particular complexes. We have also studied about the hydration of European man, and there we have seen that the luminescence spectra can also be used to find out the number of water molecule into the primary hydration sphere. And for that, one used to measure something called decay half-time. And I've shown you that for measuring this decay half-life and decay time, you have to excite at certain wavelength, and then you have to measure emission at a certain wavelength. And that should be done at a given wavelength, at given excitation wavelength, at given emission wavelength. So once you have a certain wavelength, let us say for europium, the excitation at around 394 and emission at 612, you'll get some kind of curve like this, which you follow with time. Once you get this kind of curve, what you have to do, you have to just fit this curve using a mono exponential decay lifetime. So what is that decay? You have curve that is intensity here, intensity, and time is here. You are measuring time, suppose in millisecond or microsecond. So the curve is like you have a exponential to the power minus t, that is your x-axis, into decay constant, that is. So the equation is like a exponential minus t, that is the time on the x-axis, into your decay constant, that will give you the intensity. This is for the mono exponential. Similarly, we can write for the bi-exponential or the tri-exponential, and from there you can get information about KOBS, that is the decay observed decay constant. And from this observed decay constant, you can have idea about the number of water molecule in the primary sphere. How we can get that idea? Because we are having certain relationships. So suppose you take about europium, we are having a relationship between number of primary hydration sphere, water in the primary hydration sphere, and your observed decay constant. Here you have to take care that all these values are given in milliseconds. So suppose you have a lifetime of 100 microsecond. So before using this equation, you have to convert this microsecond to the millisecond. So you have to convert that before using this equation. And once you do that, you can put the equation in this, and for 100 microsecond, you will be getting around 8 to 9 water molecule. So directly using this relationship and the knowledge of decay constant, you can get the idea about the number of water molecule in the primary hydration sphere. The graph here shows that the variation in the primary hydration sphere, number of water molecule in the primary hydration sphere, with the pH, where you are titrating a given metal ion. Here the metal ion taken is the curium. So suppose you have curium and you are titrating, you have added some ligand, any ligand you can choose here. Suppose you have added that ligand into the system, and now you are varying the pH. What will happen that when you are varying the pH, a pH will come when the ligand is more and more deprotonated, and the moment is deprotonated, what will happen? Suppose curium is having 8 water molecules here around them, and your ligand is deprotonated and it has 2 sides. So now it can attach to the metal ion and it can remove 2 water molecules. And since it is removing 2 water molecule, so whatever is there in your aqua complex, you will get a decrease of 2 water molecule. So depending on the nature of ligand, that can happen at a different pH. For example, in the first 2 ligands, you can see that even at pH 2, the complexation is so strong that almost all the water molecules has been removed, whereas for certain other complexes such as NTFC, nitrotriacetic acid, this is not that straightforward. So it is a stepwise removal of the water molecule. So just by doing the lifetime spectroscopy, you will get this kind of information in changing number of primary water molecule using different ligand in a set of pH conditions. And this table is also showing you that for a given ligand, depending on the stoichiometry of the metal ligand complex, how many water molecules are possible. So suppose I give you ligand that is again nitrotriacetic acid, and I assume that it has a stoichiometry of 1.1. So if you have a stoichiometry of 1.1, how many water molecules should be there in the primary sphere? And you can just follow the equation that is given on the top, that from this you can always get the information about the number of primary water molecule into the metal hydrogen sphere. So with that, I would like to end. Thank you very much for listening.